Okay, so we are discussing the PWM techniques, and here we are discuss the more details of how the switching is happening and what are the dynamic characteristics of IGBT and how it affects the performance of PWM converter. So we try to understand that what is switching frequency, and with respect to fundamental frequency, if we have to generalize the switching frequency, the term pulse number could be a very good tool to understand. So if you say that pulse number is certain value, so we can say that whether the quality is of the waveform, output waveform is going to be good or it's going to be normal. So these things we can guess about the performance. Now, then we have seen that how the IGBTs are going to behave when you are applying PWM voltage. So certainly when we have the ideal switch, the transition from on to off or vice versa, these states could be instantaneous. But when we have a real switch, this may not happen instantaneously. So there could be a possibility that if you are trying to give the PWM of top and bottom switches just as no an opposite of each other, let's say taking a knot and simply applying the PWM voltage, there may be a condition of shoot through between the two devices. So one may not have turned off properly, and other may turn on during the same time. So there could be a shoot through to the DC bus or across the DC bus. So to avoid all this, we need to have dead time or blanking time in the converter. So what we do, the incoming pulse is delayed by certain time. So everywhere if you see the falling edge is remaining at the original place, but the incoming pulse is delayed. So here also incoming pulse is delayed for both top and bottom switches. So by this what we will ensure that when one device is completely off, then only we are trying to turn on the other device. So in this process, what we have understood that during this dead time, we may have the possibility that the transition of current might be happening only between the IGBT and diode and never between two IGBTs. So whenever both the devices are off, the diode will support the flow of current. And let's say if the flow of current is opposite to the turned on device, then again the diode will be there to support that. So always the transition between the IGBT and diode takes place in any scenario. Let's say we consider inductive load. So current is always changing from IGBT to diode or diode to IGBT. Now with this, we try to understand the turn on characteristic of the device, and because the KVL KCL has to be satisfied always. So when you are trying to turn on the IGBT and the diode is conducting, the bottom diode is conducting over here, current is going out. So the moment there is fall in voltage, the rest of the voltage should appear across the diode, but that is only possible when the diode is not conducting. So that's why there is sudden shift of current from diode to IGBT. This we have understood, and we see a slight overshoot on the IGBT current because of the reverse recovery current which is there on the diode. So we saw this on actual screenshot or the scope capture of the converter. Okay, I think it's moving with the, okay, yeah, it's stable now. Yeah, here. So same thing we have seen over here when we captured just an instance of turn on for the device. So VC is initially high, and once we apply the gate pulse, the gate signal basically we are applying, which is this signal S. So it does not change anything immediately in the system because every system has some lag. So only after certain time the gate emitter voltage has changed to certain value, and once it stabilizes to certain normal value, then VC starts dropping. And it doesn't fall to the zero value or to the very minimum value directly. It stays for certain time in the middle, and this is called basically Miller plateau, which I have discussed yesterday. During this Miller plateau, the current changes So the normal current is here if you observe, but there is some overshoot which is coming on account of diode reverse recovery, which we have discussed yesterday. Now, the important thing to observe over here, before the device was turned on, there is very minimum energy loss across the device. This red curve is giving the energy loss in the device because product of voltage and current is nearly zero. And again, when the device is turned on, then also the voltage has gone to a very low value and current is something. So overall the product is very close to zero. But during this transition time, we have significant amount of loss in the device, which is called as switching loss. Particularly, we are looking for the turn on operation. So this is associated with turn on switching loss, we can say. So this is what we have tried to understand. Any questions in this so far?
What
Are there any questions? Yes, someone is asking something.
What is the cause of this Miller plateau?
There is no cause. It is the nature of the device. You need to understand the device physics a little bit more to understand why Miller plateau is coming, but this is generally the characteristic of all the devices, be it MOSFET or IGBT or anything. We observe this phenomenon. Fine. What happened? Yes or no? Shall I go further?
Yes, sir.
Yes, sir.
Okay. Sukumar, something?
Sir, yes, sir. Go ahead.
Okay. So now we are looking for the turn off of the IGBT. So basically when we say this, we are looking for turn off transition. That means the device is on, and then we are going to have current transition from the device to the diode. So again, we have to ensure that KVL, KCL are always satisfied. These are the most fundamental principles. This can never be violated. So what we see over here is that we have current, which is say at rated value, flowing through the device and going out of the converter. And this is where we are trying to remove the gate pulse at this instant. So what will happen? Removing the device or removing the gate pulse from this IGBT will basically reduce the current slowly and it will take it to zero. So we will have two types of slopes observed in the IGBT. So this is one main little longer tail, this current would be this, and this will be something like a tail current. So this will be observed, this kind of behavior is observed in IGBT. So what we have basically that the moment there is even slight reduction in current over here, that current which is subtracted from the device basically comes from the diode or comes through the diode. In that process, the diode has to conduct, and the moment diode conducts, there cannot be any voltage across this, which means the device voltage will jump to maximum blocking voltage, and still the current will be dropping slowly. So this is how typical the characteristic of turn off characteristic of IGBT would look like. So voltage may see very sharp, very steep rise over here, and the current would fall progressively. So we can observe again, say a lab capture or something. So important thing will be to notice the time here. And particularly this is a bigger device, so the time scales are very easy to understand. Okay, maybe perhaps I will mention the time scale over here first. So here we are observing, let's say each scale or each division is something like 0.8 microsecond. So from the moment you have applied the gate pulse to the point where this current stabilizes, this could be something around 4 microsecond or so. Correct? And VC might have gone 0 at this point, which is something around 2 microsecond or so for this particular device. Understanding the time scale? This I am talking particularly from the point of view of this high power device, which is having rating of 4500 volts and 1200 amps. These are industrial devices, which is typically used in, let us say, railway traction converter. So Deepak might have encountered in that. So this is Infineon device. These kind of devices are basically used for megawatt converters and such kind of power level and high voltage level, or say medium scale voltage level, which basically goes beyond 1 kilovolt. So this is what we have here. Now for the turn off, because the duration is much bigger compared to turn on, we have applied the gate pulse here, and before that the gate emitter voltage is say high. We are removing the gate pulse over here, and current is somewhere here, say the rated value. This is the 0 for the current. Now once we apply the or remove the gate pulse from the controller, then the gate emitter voltage starts changing and then slowly falls to 0 value, or actually negative. To maintain good performance and fast turn on turn off, it is maintained negative. So 0 might be here somewhere. So what will happen in effect? The current, if you observe, this has not changed much. It is almost flat. And within that duration, the voltage has gone up to the highest value. You see the change over here? This change in voltage is much steeper compared to the current, and which is what is expected. Even if the diode is conducting 1 ampere current, this current level, by the way, is something close to 1200 ampere. So even if the diode is conducting 1 ampere, the voltage cannot be non-zero across that. So that's why there has to be steep rise in the voltage. You understand this point? And after this has reached the full value, then actually current starts falling, and then this tail current behavior, what I was mentioning earlier, comes into picture, and then it goes to 0. Are you able to see this? Now we have one more overshoot on the voltage coming over here. This basically comes on account of the rate of change of current. So if you observe, this is where the current has started changing, this instant. So there is some di by dt associated with this fall in current. In response, whatever inductance you have on the bus plate or the bus bars, that will give some overshoot on the voltage. You understand this point? You understand this point? There may be some very small inductance, let's say 100 nanohenry or something. This inductance basically causes this kind of overshoot over here. So the total voltage, whatever is there across the device, what it's going to block, plus this LDI by dt, what is coming on account of this inductance and the fall in current. These two give additional overshoot on the voltage VC, and then it settles. It's not a very fast device, no, because high power devices are generally slow, so we do not see much overshoot compared to the rated voltage. This voltage is somewhere around say 2 kilovolt or 3 kilovolt something. We don't see much because this response is much slower. For low power devices, when di by dt is much larger, then we can see much higher overshoot, something like this, and there could be ringing phenomena also. But here we don't observe that. It's a very neat and clean waveform because device is little bit slow in nature due to its high power ratings. Now, the important point to notice over here is this scale now is 2 microsecond. So from the moment you have removed the gate pulse till all these waveforms settle, this could be something like 10 or 12 microsecond. Now you can understand why we need to turn off the device first and then turn on the next device. Because turn off process is slow. It may take longer time to turn off, and within that we may turn on the device and there could be a shoot through. You understand this point? Which is why we need to have first turn off the device, then let the current get transferred to the diode, and then you turn on the other device. So have sufficient margin. Now, if you ask me for this device, when this kind of time scale is coming, 12 microsecond for turn off and let's say 3-4 microsecond for turn on, what should be the dead time? I would say straight away go for 20 microsecond this dead time, which is a very big number actually. You understand the point here?
Yes, sir.
And the red waveform which is shown here, which is having zero value before the device has before the device has gone into off mode or after the device has gone into off mode. Both places this is very close to zero. But during this transition there is very sharp rise in energy and then it is falling back. Or power we can say. So this whole curve what is given over here, whatever area it is occupying, that is all total power loss in the device during turn off. So we can say turn off power loss or switching energy loss. You understand the point here? It's fine or not?
Yes, sir. Yes, sir.
Yes, sir.
Clear? Now, when we have this understanding, so what we are able to say from all this is that definitely there is some energy loss involved with the device transition. So we can say two instances it may have where or it will have where we will have the power loss or energy loss in the device, and that is one during the turn on, another during the turn off. This combined is called switching energy loss. And from the waveforms you can understand this E on or E off, any of this is basically if you have very high say DC bus voltage, then the area will be larger, that is covered by this graph. If you have very high this VC or very high DC bus voltage, it will rise for a longer time and cover much larger area, right? Fine, right? So one parameter where this energy is dependent on, this is VDC. Another parameter on which this energy is dependent on the rated current. Of course, it is changing in the sinusoidal cycle. So you can take something like the RMS or average, whatever average of the half cycle. So you can consider that for computation. Then there is another thing which is transition time. If transition time is more, you have more energy loss. The area is bigger. If this is large, then you are going to have the loss for a very long time. So something like this. So I'm talking about the area of this graph. So these three parameters are affecting that in one switching transition, how much this is going to be. Now, if you have to repeat this process, you have to repeat the turn on, turn off several number of times, let us say hundreds of times. So then what will happen? You will have more loss during the fundamental cycle. Let's say this is the fundamental cycle and you are switching at least 1000 times in one cycle. So if your fundamental frequency is 50 Hertz and your pulse number is say 1000 roughly, then your switching frequency is something like 50 kilohertz. So you can imagine how much loss you are going to have in the device during switching. Particularly for high power devices, we do see that the switching energy loss is higher compared to the conduction energy loss. Or let me change it to power. So if you multiply this factor switching frequency to this term, this basically results into a quantity which can be related to power of the power loss in the device, FSW. I am writing proportional because it's not exactly equal. The current is changing, it's sinusoidal. And there are some more things involved in that. It's not a straight away product. So some proportionality constant could be there. Now, this power loss during switching is straight away proportional to these parameters over there. Conduction loss we have seen. You have computed in other assignment that it is proportional to VC, SAT, and whatever current is flowing through that, or V blocking into I leakage. So this may be ignored. Primarily I conduction, P conduction is this. For a system when we are designing, when we look at the parameters, we don't have much say over this VC SAT. Once you choose the device, it is done. Maybe 2 volts, maybe it's some 2.5 volts or 3 volts, it is done. You cannot do much over this. The current also is more or less dictated by the system. What is the power level, let's say megawatt power level or few kilowatt power level, your current is more or less fixed. So conduction loss in a way is kind of fixed the moment you take a system or choose a system. Choose a converter, choose a motor, your conduction loss is more or less fixed. But here the switching energy loss is still having some variables which are there. So apart from these three quantities, very important quantity which is switching frequency, this is not at all dictated by the motor or inverter or anything. It is up to you. Based on what quality of current or voltage you want to have, you can have any value of this FSW. Other things are fixed. VDC is fixed with the system, I rated is fixed, transition time is fixed with the device. So this is where we need to understand that how much switching energy loss or power loss we can have in the system. How much we can tolerate. So particularly when we talk about the megawatt power level systems, okay, or maybe I will just bring up another graph to understand first the application of drives, then you will have a better view of what is happening. Okay, I can't bring it here. Okay, let me copy. How to import this here? Okay. Yes. See, this is one typical graph I have tried to plot for the applications what we may have in motor drives, particularly let's say induction motor. So we have power on one axis and the rotational speed on the other axis. So basically rotational speed is kind of related to the fundamental frequency. So you can say power versus frequency graph. This is. So what we have in this graph, the applications such as let's say oil and natural gas compression, when we have the oil industries or these kind of industries, they basically transmit the oil or natural gas from one place to another place through pipelines. So hundreds of kilometers they will have pipelines laid down and they will just compressed from one end and it will run to the other end. So to keep that pressurized, we need compressors, and these are really high power compressors which are used. So scale, you can see this is coming something like 10 megawatt kind of system. So here the current may go something like 2 kilo ampere, which is a very high current. Now we have another application where we have aircraft propulsion. So power may be high, but at the same time, we may need to have high speeds also. So some amount of aircraft propulsion may come over here as well on the high speed side. Power may not be required to be very high. For example, sophisticated drone or something, the speed need to be very high for the propeller. And then we have railway traction. Here the typical power rating is something like 3 megawatt for the total system and 850 kilowatt for the motor, or sometimes we have 1.1 megawatt motors also installed on the trains. So all these electric locos what you see for running the goods and passenger trains, these basically have these kind of induction motors. These are called traction motors. 850 kilowatt or 1.1 megawatt rating. So these kind of motors are available. On the other hand, so for all these applications which I am saying here, the speed is not very high, something limited to 5000 RPM. So we can say low or moderate speed kind of application. Now, other hand, if we go, the power comes down. Power becomes something like say 500 kilowatt max. But the speed may go all the way up to 500,000 RPM, which is a very high speed. When we are running some spindle or some other micro turbines or air compressors, or in fact some aircraft propulsion. So in all these cases, we may see that our fundamental current, or sorry, fundamental frequency is going as high as 2 kilohertz. You see these applications? That is how you will find the industrial drives present over there. We may have something available for this zone as well. Okay, but this will have properties of both these zones. So broadly, we can classify that this may form one zone where we have moderate power but very high fundamental frequency. Another one may be here where fundamental frequency may be restricted to little lower value, but the current is very high or the power is very high. Now, what is the result of that? What is the consequence of that? Having such current level and such fundamental frequency. Obviously, the current, you can relate that straight away it will have very high switching energy loss if you want to have any system. So switching energy or switching power loss will be very, very high for all such systems. So definitely to control switching frequency loss, or sorry, switching energy loss, we need to bring down the switching frequency to a very low value. So irrespective of what system you have, what fundamental frequency you have, sometimes you have a hard, you may have a very hard restriction on the switching frequency that you cannot cross this boundary of 750 Hertz. Irrespective of what fundamental frequency you are running at, this may be a hard boundary. For railways, actually, this is 350 Hertz or 500 Hertz. You understand the point? So one is this applications where we have very high power level. So to reduce this or keep switching energy loss in control, we need to reduce the switching frequency. Otherwise, the converter cannot run. It will simply burn out. You cannot control the energy or the heat or the temperature inside the module. It will simply burn out. Understanding my point? Now, the second part where we are having very high fundamental frequency. So obviously, we are increasing our fundamental frequency. Now to have good waveform quality, we should have high switching frequency as well. But there is definitely a limit on maximum switching frequency when you take any device, let's say IGBT. For reasonable power level, the switching frequency may be restricted to only 10 kilohertz. You understanding my point? There is some transition time related to going from on to off and then from off to on. We cannot have any time period which is lesser than this transition time. We need to give the device adequate time to turn on and turn off properly. And that is why we cannot force very high switching frequency on the device. And this transition time increases with power level. You understand these statements? So despite this fundamental frequency, we are not able to keep the switching frequency very far from the fundamental frequency. This is also kilohertz, this is also kilohertz. The ratio is only 5. So both these applications are strong examples of where we need to have pulse number, say below 9. So sometimes it could be 3, sometimes 5, maybe 1 also sometimes, 7, 9 and so on. You cannot go beyond these numbers. The system or the IGBT or the switching laws, the heat sink design, this will not permit it to go beyond that. You remember pulse number, right? Switching frequency by fundamental frequency. Clear? You are getting the understanding? Now, apart from, let's say, these are some of the industrial drives which are involving high power, high speed and all that. But not every motor drive is high power or high speed. There is something like which lies in, say, this zone. Okay, I can draw with black. Let us say this small zone. So if anything lies here, then okay, we need not have any restriction on the pulse number. Say if my motor is only 5 kilowatt and the fundamental frequency is 50 hertz, then no problem. I can simply run at 5 kilohertz switching frequency. What's the problem? So here my pulse number will be something like what? 100 or close to that. Understanding my point? So based on different applications, we need to see that which type of PWM technique is good for which system or which motor drive. So certainly when we are talking about these kind of applications where pulse number is below 9, we should have something which we have studied so far, say SHE PWM or optimal PWM. These kind of low switching frequency PWM techniques are very suitable for these applications, even here as well. You understand the point? So any of this condition is satisfied, we need to have this kind of pulse width modulation technique. Now someone may ask why not we are having high switching frequency devices, let's say silicon carbide or gallium nitride and all that. Yes, that technology is coming up, but still it has not reached the maturity level of IGBT. It is still a little bit far from there. So yes, researchers are developing, but as we are developing better devices, say silicon carbide or something which can go up to 100 kilohertz of switching frequency, we are finding many different challenges for this as well. And in fact, in a quest to increase the power density, this is further extending. This is also further extending. So the need for this PWM may not end so soon. It may be there for a very long time. You understand the point? Correct?
Sir.
Good.
Yes.
So apart from all this, whatever I have drawn here, this big zones, whenever you have power levels restricted within say 5-10 kilowatt or 20 kilowatt, maybe smaller box I can draw, and normal fundamental frequency 50 hertz, 60 hertz, even 100 hertz, that's also fine. You can go for pulse numbers which are higher. And then actually we need not go for the PWM techniques like SHE PWM or optimal PWM. We may have something better. Correct. Better in terms of the waveform quality. So that is where we come to other means of converting our DC voltage to AC voltage. One method we have done, simply having this square wave kind of waveform and then putting a notch and just going on increasing the switching angles within the quarter cycle. But we may have an entire different philosophy of converting DC voltage to AC voltage instead of this what we have done so far. And that is where we come across the PWM techniques which are like sine triangle PWM or conventional space vector PWM or sometimes third harmonic injected PWM and so on. There may be many more. All this can be called as high switching frequency PWM techniques. So we are ensuring that our switching frequency and fundamental frequency are little bit far. At least pulse number is greater than or equal to 21 to get the real benefits of these high switching frequency PWM. Fine. So I stop the class over here. Next class we will start with sine triangle PWM.